This is the 6th video in a series that I'm creating for abstract linear algebra. And we've finally explored enough mathematical objects in order to efficiently look at the notion of a vector space. And vector spaces are one of the main objects of study in linear algebra. Okay, so let's look at the definition. So we want to start with a field K. So we'll suppose that lowercase k is a field and V is a set together with two operations. So the first operation will be labeled as addition. We'll often call this vector addition, and it will take two vectors and give us a single vector. So in other words, if we've got V and W in V, well, we call elements of V vectors, by the way. So we can add V plus W and we land back in V. Next, we've got an operation which takes one element from K and one element from V and gives us a new element from V. And by the way, elements from K are often called scalars, and this operation is called scalar multiplication. And so we generally write it as follows. If we've got a vector V in V and a scalar alpha in K, then alpha V is in V. So this is the scalar multiple of V by alpha. That's maybe how we would say that. Okay, just to reiterate, this is vector addition. It allows us to add two vectors. And this is scalar multiplication. It allows us to multiply a vector by a scalar. So notice one thing that we don't have here is vector multiplication. In other words, we cannot multiply two vectors. Now, if we, in addition, had that kind of structure, that would be something called an algebra, but we don't have that type of structure at the moment. Okay, so finally, after the setup, so a field and a set with these two operations, we say that V is a vector space over K if for all alpha and beta in K and V and W in V. So in other words, scalars alpha and beta and vectors V and W, the following four conditions hold. So the first condition is that if we just look at V together with the vector addition operation, that forms an abelian group. And I've written here in parentheses an additive abelian group because we write that like it's addition. And then next, we've got this associative rule for scalar multiplication and regular multiplication. So it may look like nothing's going on here, but if we look carefully at the parentheses, something is. So over here on the right-hand side, what we have done is taken the scalar multiple of V with beta, then that gives us a new vector. We take that vector and do the scalar multiple with alpha. And that should give us the same thing as first multiplying alpha and beta in the field, and then taking the scalar multiple of V by that number. Okay, so just to reiterate, here we have a scalar multiplication within a scalar multiplication. And over here, we first do multiplication in the field, then scalar multiplication. Okay, and then finally, we've got the following two distributive rules. And so our first distributive rule says alpha plus beta on V is the same thing as alpha V plus beta V. Again, we have to look at this very carefully. Over here, we're adding two scalars, so that addition is occurring within the field, and then we're doing scalar multiplication, whereas over on the right-hand side, this is vector addition. So we first do scalar multiplication of alpha with V and beta with V, and then we do vector addition of those two resulting vectors. Okay, so we've got one last distributive type rule, and that would be alpha on V plus W is alpha V plus alpha W. Okay, and so this one is not actually quite as tricky as the one before because we've got vector addition occurring here and vector addition occurring here. It just says that the scalar multiplication distributes through the vector addition. Then finally, we've got this short one that says 1V is equal to V. And by 1V, I mean the scalar multiple of the number 1, which is in the field. That's the multiplicative identity of the field, should be equal to the original vector. In other words, scaling a vector by 1 should not create a new vector. Okay, so let's look at some examples, and we'll go through most of the details for proving that these are vector spaces, at least for the first several examples, so that you can check the others on your own. So the first example I want to look at is maybe the most boring, but it's often really important to look at the trivial example first, just to realize how simple a structure a definition can kind of condense down to. Okay, so let's take our set to be equal to the singleton of 0. And you might say, well, where does this 0 come from? Well, you could think of it first as just kind of a symbol 0, or you could also think about it as being the additive identity from any field. It's really up to you. You get the same sort of structure no matter what. And then this, in fact, is something called the trivial vector space. And it's a trivial vector space over any field if we define the following. So define the scalar product of alpha with 0 to be 0, which makes sense. If you multiply anything by 0, you should get 0. And now we can notice that these 4 conditions are satisfied. This is most definitely an abelian group. Notice that it has an identity with addition. The identity is just itself. So if we add 0 with 0, we get 0. That means 0 is also its own inverse. And then you can also check that you get associativity out of that as well. Okay, and then all of the rest of these are satisfied as well. So let's go ahead and take an element from V, but there's only one element from V, and then check this second one. So if we have alpha times beta 0, that's the same thing as alpha 0, which is 0, because beta times 0 is 0, but that's going to be the same thing as alpha beta times 0. Again, by the definition of our scalar multiplication. I should point here that this is for all alpha in our field K. Okay, so now let's maybe check some of the others. Let's maybe check this one right here, and then we'll kind of leave it at that. So let's say that alpha and beta are in the field and V is in the set V, but that's just a singleton again, so there's not really anything to do there. So if we have alpha plus beta times 0, scalar multiplied into 0, we get 0, but that's the same thing as 0 plus 0, but that's the same thing as alpha 0 plus beta 0. So we haven't quite checked everything over here, but I think we've checked enough to see that this does satisfy all of these conditions over here. So that makes this into something called the trivial vector space. So I'll just say that this is the trivial vector space, and that's over K. Often we use this slash to just shorten the word over. So this is the trivial vector space over K, where K is any field at all. And like I said, you can take this 0 one of two ways, just as a symbol that satisfies these two rules right here, or as the additive identity within the field itself. Okay, so now that we've got this trivial vector space taken care of, let's maybe bump up and look at maybe the next most simple example. So for our next example, we'll let K be any field. And often for these, we'll let K be any field, although we will look at some special examples when it's appropriate. Let's just recall which fields that we know a lot about from previous videos. So this could be the rational numbers, this could be the real numbers, this could be the complex numbers, or this could be the integers modulo P, where P is a prime. We call that FP when we're working in the setting of a field. So that's our field, and then we'll let V just be equal to the field itself. And we often say here that K is a vector space over itself. Great. And now we need to define we'll need to define vector addition and scalar multiplication. So let's define vector addition just as addition in the field. So in other words, we've got an addition within K, and since V as a set is just equal to K, well, that's exactly how we will define the vector addition. So if we take V and W in V, notice that means that V and W are in K, but that means that we can define this V plus W is also in K. Okay, nice. And then how will we define scalar multiplication? Well, we can define scalar multiplication just as multiplication in the field itself. Okay, so notice if we've got an alpha in K and a V in V, because notice that's what we need for scalar multiplication. Well, the fact that V is in V tells us that V is in K, which means it makes sense to multiply alpha with V. We have alpha times V is most definitely in K, but again, K is equal to V, so that means alpha times V is in V. And we have that multiplication defined. And now you might say, well, what about all of these conditions? Well, notice that all of these conditions follow very, very, very quickly just from the definition of a field. So this first one is actually baked into the definition of a field itself. And so is this one right here. This is the associativity of multiplication. And this distributive rule is also baked into the definition of a field, as is this down right here, which says that every field has a multiplicative identity. So there's not really anything to check here because we already know these things hold from the definition of a field. Okay, good. So let's maybe keep going. Okay, so now let's again start where K is any field, and we'll set V equal to, I'll call this K2 or K squared. So what I mean by that is the Cartesian product of K with K. In other words, all ordered pairs, A1, A2, where A1 and A2 come from K. So the set of all ordered pairs. So often we write these as columns, and that's actually how we'll mostly write them, just because that will work better with some of the structure that we do later. So instead of writing this as an ordered pair, I'll write this as a column where we have A1, A2 like this. Again, A1, A2 is in K. But it's just really a different shape of the whole thing. Okay, so now we know what our set is. Our set is all symbols like this, where A1 and A2 come from K. And now we need to define vector addition and scalar multiplication. So we'll define vector addition as follows. So we have, so let's say that V is equal to A1, A2, and let's say W is equal to B1, B2. So that makes both of them elements from V. Now we'll define V plus W to be, well, that's A1, A2 plus B1, B2. Well, we'll define this so-called component-wise. So everything in the first entry of the column we will add, and everything in the second entry of the column we will also add. So we have A1 plus A2, and then B1 plus B2. Okay, so now we'll make the following claim that V with plus, and by plus I mean this operation right here, is an abelian group. Okay, so notice we need to check associativity, we need to check inverses and all of that stuff. So let's maybe do those one at a time. Well, we definitely have an identity element, and that identity element is the symbol 0, 0. And that's because 0, 0 plus A1, A1 is equal to A1 plus 0, which is A1, and then A1 plus 0, which is another A1. So that means this guy right here is the identity element. Oh, and I'd like to point out here that we should be a little bit careful. This addition is the vector addition, but when we put it in this column, this addition is the addition within the field. Okay, great. So now what about inverses? Well, the inverse of A1, A2 will be equal to exactly A1, A2. And I should maybe have A1, A2 here instead of A1, A1. So let's notice that if we take A1, A2 plus negative A1, negative A2, we'll definitely get 0, 0. So that makes these two guys additive inverses. And now there's one more thing to check, which is associativity. So maybe make sure to keep in mind that we haven't checked that, and that'll be part of the warm-up exercise to check everything that we haven't carefully checked. Okay, so we've sorted out vector addition. Now we need to sort out scalar multiplication. So for scalar multiplication, we need to decide how to multiply a single scalar from K to a vector V that is of this form. So let's see how we might do it. Let's take alpha to be from our field K, and then we'll take V to be equal to A1, A2 from our vector space, or our would-be vector space V. So it's written as a column like this. And then let's define our scalar multiplication as follows. So alpha on V, well, that's going to be the same thing as alpha on A1, A2. And then we do this maybe just the way that you would guess, and that is to distribute this onto both of the entries. So this will be equal to alpha A1 and then alpha A2. So let's see. For example, let's say we're working over Q2. Well, we could look at something like this. 2 times 1, negative 3, plus 5 times negative 2, and then 4. So that would be an example of some vector operations within this space Q2. So notice we've got scalar multiplication of 2 onto this vector 1, negative 3. And then we're adding that to scalar multiplication of 5 onto that vector negative 2, 4. Okay, so let's start by doing the scalar multiplication. That will give us 2, negative 6, plus negative 10, 20, like that. So again, that's from the scalar multiplication. And then finally, we can do our vector addition. That will give us a minus 8 in the first entry and a 14 in the second entry. So there's just a nice example of how these operations work with like concrete numbers. Okay, so now let's maybe check one of these conditions over here involving our scalar multiplication as defined here and our vector addition as defined on the last board. Okay, so now let's check that these distributive rules hold, or maybe we'll just check this first one. I'll leave this one as, like I said, a warm-up exercise. So let's take alpha and beta in the set K, so that's our field, and then we'll take V, a vector, so that means it's of the form A1, A2, and that comes from our vector space V as defined above. And now let's look at this. So we'll do alpha plus beta on V. Notice that's the same thing as alpha plus beta on A1, A2. But now thinking about this as just a number, scalar multiplied into that, that's going to multiply into each entry. So that'll give us something like alpha plus beta A1, alpha plus beta A2. So that's by our definition of scalar multiplication. Cool. Now we can take this and use the distributive rule which occurs within the field. Remember, we know that the distributive rule works within the field by the definition of the field. So this is going to give us alpha A1 plus beta A1, and then alpha A2 plus beta A2. Again, doing the distributive rule in each of those components. But now we can start to pull this apart. So this is the same thing as alpha A1, alpha A2 plus alpha B1, alpha B2. That's by the definition of vector addition. And then finally, we can bring the alpha out. This is alpha A1, A2 plus bringing the beta out, B1, B2. And that's by the definition of scalar multiplication, like in reverse. Finally, we can write this as alpha V plus beta V using our original notation, and see that the extreme left-hand side and right-hand side gives us exactly this condition over here. Okay, nice. So now that we've got this, I want to look at the geometry of K2 for some special fields K. Okay, so here's a nice geometric representation of R2. So that's all ordered pairs with real numbers, but we're going to write them as columns. So I've put my Cartesian coordinate plane here. So we might think that this guy right here has everything of the form x0, so this x-axis, but we might write that, like I said, as x comma 0 in this case. So that means everything where the second entry is 0 is along this horizontal line. And then up here, everything is of the form 0y. So everything along this vertical line, the y-axis is of the form 0 comma y. So in other words, the x-coordinate, or the first coordinate, is 0. So let's look at our vector v, which is 3, 2. So if we go to our coordinate 3, 2 in this Cartesian coordinate plane, we can draw v as an arrow going from the origin to this point right here, which is the point 3, 2. Now we might think about this coordinate right here as being the coordinate 3, comma 2. This is maybe a useful way to think about it, is that the point is the actual coordinate that you learned about maybe in high school algebra, but the vector is really like the action of going from the origin to that point. So the vector is really kind of this arrow pointing from the origin to that point there. Then we've got another vector, I've called it W. It's 2, 4. And so that means that it will be the action of going from the origin to this point 2, 4, like this. Now let's see what we get for some scalar multiples of maybe V and W to get some geometric intuition for that. So let's first maybe look at 2 times V. Notice that's 2 times 3, 2. That will be equal to 6, 4. Okay, nice. So let's go ahead and graph that. So that means we need to go 4, 5, 6 along this horizontal axis, and then 4 along this vertical axis. So that will give us a point that's right about here. So I'll maybe put this in just a dotted thing to say that it's related to V. So that's our new vector 2v. So I'll maybe put this as 6 comma 4. So that's like the coordinate. And then we'll say that this whole thing here is like 2v. So that gives us some intuition for what scalar multiplication does. So in this geometric situation, scalar multiplication will maintain the direction of the vector, but perhaps change the length. So in this case, the length was doubled, but it's along the same line. Now, what if we did something like 1/2 W? Well, let's do that. So 1/2 W, that's going to be half, and then 2, 4, but that'll give us 1, 2. So let's graph that. So 1, 2 is like right about here. So let's fit that in. So we've got 1, 2. And notice that that will be this vector right here. So let's just notate it like this. This is 1/2 W. So let's notice that that's on the same line as well, but instead of scaling it so it's longer, we've scaled it so that it is shorter. Okay, let's look at one more, and that would be maybe negative V. So negative V, so that's going to be the same thing as negative 3, negative 2. You could also think about that as the scalar multiple with negative 1, although we'll prove that carefully a bit later. Okay, so let's see, that's going to be over here, negative 1, negative 2, negative 3, and then negative 1, negative 2. But as you see, that is exactly what we would get if we move in the opposite direction of V. So here, this would be like negative V right here. So that starts from the origin and goes to the point which has maybe been reflected across the origin from the terminal point of V, if you will. So just to reiterate, here is negative V, like that. Okay, nice. So let's maybe put one more thing on here just to get a full idea of how this is working geometrically. And here we'll look at v plus w. So notice that that is 3, 2 plus 2, 4. That's going to give us 5, 6. Okay, so that means we need 6 along this vertical axis. Then we need to go to 5 and 6. So that's like this point right here. I'm going to do this in a different color. So this point right here, this is like 5, 6. Great. And we can visualize this one of two different ways. We can visualize this by going to the end of V and then following W. So I'll put this in a dotted line. So this is like W where it's been transposed so that the origin is at this terminal point of V, or likewise, we could go to the terminal point of W and follow V. So something like that. So notice we complete a parallelogram. But if we were to put this all together, we would get the diagonal of the parallelogram. So this vector right here would be the vector v plus w. Okay, nice. So I think this is a nice visual representation of what's going on when we do vector addition, especially in this R2 case. Let's maybe like clean up the board and we'll look at a similar example for a finite field. Okay, for another example, let's look at F3, 2. So in other words, this is going to be the set of all vectors with 2 entries, and those entries come from F3, the field of 3 elements. Let's recall the field of 3 elements is the numbers 0, 1, and 2, where both addition and multiplication occur modulo 3. So for instance, 2 times 2 is 4. We divide that by 3 and keep the remainder. The remainder is 1, so that means 2 times 2 is in fact just 1. So in a previous video, we made multiplication and addition tables for this type of structure. I'll let you guys look back at those if you need to. Okay, so let's see what's going on in this case. Here we can draw the picture just as this grid. And vectors cannot end anywhere except for these lattice points. Notice that there are exactly 9 points that vectors can end at. That's because there will be 9 elements in this vector space. So here, this is where the first coordinate is 0 and the second coordinate is 0. First is 1, second is 1. First is 1, second is 0, and first is 2, second is 0, and then so on and so forth. So here's an element of the vector space. So it's 2, 1. So that's going to be the vector that goes from the origin to this point right here. So we might think of it like this arrow. So it's starting there at the origin, and then it's ending at that point right there. Likewise, we could have a vector w, which is 1, 1. So that would be like going from the origin to here, this point 1, 1. That would be like w right there. Okay, nice. So now let's do some examples of scalar multiplication and addition here. Notice there are really only 3 scalar multiples of v. And that's because you can only scalar multiply by an element of the field, and the field only has 3 elements. So we can actually write all of these down. So scalar multiples of our vector v. So we have 0v, but that's just going to be the 0 vector because anything times 0 is 0. Or we could have 1v, but that's just our vector that we started with, 2, 1. Or we could have 2v, but that's just going to be 4, 2, which is the same thing as 1, 2, because we reduce modulo 3. So those are all of the scalar multiples of v. So notice the 0v is not super interesting. That's the vector that starts at the origin and just stays at the origin. It doesn't do anything. 1v is the one that we've already written. And then 2v, well, that's going to start at the origin and go to 1, 2 by our calculation over there. So let's write this. That's going to be a vector that's something like this. This would be the vector 2v. And likewise, it's pretty easy to see that the vector 2w would go from 0, 0 to 2, 2. It would go like that. Okay, so let's see what the sum of the vector v and the vector w is. So we've got v plus w, so that's going to be 2, 1 plus 1, 1. But doing our vector addition, that gives us 3, 2. But let's recall that we're working modulo 3, so that means we get 0, 2, because we divide by 3 and then keep the remainder. Okay, so that means our vector v plus w starts at the origin and then goes up here, something like that. So it starts here, so v plus w. Great. So notice the geometry of this vector space F32, or really any of these vector spaces of finite fields, is quite strange. You could visualize it a little bit by taking multiple copies of this and kind of gluing them together and saying that certain edges were equal to each other. That's not really going to help us so much for our goal, so I'll let you guys look into that if you'd want to. Okay, so let's get rid of this and look at some more examples. So for our next example, we'll look at a generalization of this K2 that we saw previously, and that will be Kn. So I guess I should say here, n is a natural number. So what I mean by that is all n tuples of elements from our field K. I've written them as columns again. So we've got this column with n entries, A1, A2, all the way down to AN, where those AIs are in K. So of course we need to define the vector addition and the scalar multiplication in order to decide if this satisfies these rules of a vector space. The calculations will be quite similar, so we won't go through them in as much detail. So the vector addition will go like this. If v is equal to the vector a1, a2, all the way down to an, and w is the vector b1, b2, all the way down to bn, then we'll define v plus w to be the vector a1 plus b1, a2 plus b2, all the way down to an plus bn. So in other words, we're defining the addition component-wise. Then we'll also define scalar multiplication, kind of inspired by what we did in the case when n was equal to 2. So let's take alpha to be in K, and then we'll take v to be this guy up here. Then alpha v will be defined as alpha a1, alpha a2, all the way down to alpha an. In other words, we scale every entry of the vector by this scalar alpha. Now, again, you guys can check pretty easily that this satisfies the same rules as we need for it to be a vector space, just like in the n equals 2 case. There's not actually a lot more going on there. You just have to include this ... to finish it all off. And there's actually some similar geometric things going on as well. For instance, we have this parallelogram rule happening for vectors in R3. So let's say this is R3. So that means we've got 3-dimensional vectors. So we might visualize those like this. So there we've got a vector that's kind of pointing out in space. We could take another vector and then add them, and we'd get the same sort of parallelogram picture that we did before. Again, I won't draw the picture because it's so similar to what we had in 2 dimensions. Okay, so let's get rid of this and we'll look at some other classes of vector spaces. So our next vector space is really important. It's a vector space of polynomials. And so we could take K to be any field, and then we'll say K adjoin X. That's how I'll read that. That's the polynomial where X is the variable or the indeterminate, and K is the space where the coefficients come from. So this is everything of the form a0 plus a1x plus a2x squared up to anxn, where n is bigger than or equal to 0 and ai is an element from K. So let's see. For example, 1/2 plus 3x plus 5x squared is an element of Q adjoin X. It's also an element of R adjoin X as well as, let's see, C adjoin X. Another element of Q adjoin X would be something like 17x to the 9th minus 45 over 19 x to the 12th. Like I said, that's another element of Q adjoin X, also R adjoin X and C adjoin X, where those are complex numbers and real numbers respectively. Just to drive home that this could happen over any field, we could have two polynomials in F3 adjoin x, maybe x plus 2x squared, and then 1 plus x squared. Those are two polynomials whose coefficients come from F3. Now let's see if we add them. X plus 2x squared plus 1 plus x squared. We get 1 plus x plus 3x squared. But since we're working within F3, the integers modulo 3, this 3x squared is 0, so we get 1 plus x. So some strange stuff is going on with multiplication when we have, or with addition when we have finite fields there. Okay, so now that being said, how can we define our vector addition in general and our scalar multiplication? So it's actually not too bad. You can just use standard addition of polynomials and the distributive rule. So let's say we have f of x is a0 plus a1x all the way up to am x to the m, and we'll say g of x is b0 plus b1x all the way up to bn x to the n. So something like that. So then we would define f of x, and then by the way, maybe we'll say just without loss of generality that m is bigger than or equal to n. So one of them has to stop maybe shorter or at the same part as the other. So we would call that the degree, as you might have learned in a previous class. Okay, so f of x plus g of x. So we'll just add those component-wise, but by component-wise, I mean combine like terms. So we've got a0 plus b0 plus a1 plus b1x plus all the way up to an plus bn x to the n, and then plus all the way up to am x to the m. So notice we stopped having b terms when we got past the degree of g of x. So that would be this vector addition. And then what about scalar multiplication? Well, you might guess, like I just said, you would use just the distributive rule. So alpha times f of x, that'll be just alpha a0 plus alpha a1x plus all the way up to alpha am x to the m. So I just distribute this alpha onto all of those terms from the polynomial. Now, checking all of these things is actually quite easy, and that's because we know most of them, given the fact that these represent something called a ring, which we talked about earlier. And a ring actually has a little bit more structure than this vector space. So it inherits all of those nice properties of the ring, which give us all of these nice properties, making it a vector space. Okay, so let's maybe look at one more example, and then we'll prove a couple standard general results. For our last example, let's say k is the real numbers and v is C0R. So just to recall, that's the set of all continuous functions from R to R. So let's look at some examples of elements in this space. So maybe if we have f of x equals x cubed minus x squared, that's definitely an element from V because polynomials are continuous functions. We could maybe have g of x would be equal to sine of x plus e to the x. That's also in V because sine of x and e to the x are continuous functions. Now, how would we define the sum? Well, we would define the sum f of x plus g of x just as x cubed minus x squared plus sine of x plus e to the x. So just the way that you would add functions normally. Now, how would you define a scalar multiple? Well, let's do this via example as well. So let's say we have 3 times f of x. That'll just be 3x cubed minus 3x squared. Okay, nice. Now again, we won't check that this satisfies all of the rules of a vector space because I think we pointed towards this being, again, a ring, which means we kind of get most of these rules for free anyway. So I'd like to reiterate that the space of continuous functions, as well as polynomials, which is actually a subspace of this, are really important examples of vector spaces, and often examples that you wouldn't really think of if you looked at a more physical approach to vectors. So now let's look at a general result having to do with vector spaces. So now we're looking at a nice general proposition relating to vector spaces. So let's say V is a vector space over a field K. So this is an arbitrary field K. And then alpha is an element from K, so alpha is a scalar, and V is an element from V, so V is a vector. Then we have the following 4 results. So first is that alpha, where that's any scalar, scalar multiplied onto the 0 vector is equal to the 0 vector. And I'd like to point out that since the 0 vector and the 0 scalar look pretty similar, when there's any confusion, I'll put an arrow over the 0 vector. I won't do that all the time. I'll only do that for these kind of first examples where we're really getting used to the notation. In general, it's pretty easy to see by context which is a scalar and which is a vector. Okay, so anyway, alpha times the 0 vector is equal to the 0 vector. So let's prove that one. So let's notice we've got alpha times the 0 vector. That's going to be the same thing as alpha times the 0 vector plus the 0 vector, given that the 0 vector is the additive identity for V as an additive group. But now we can use our distributive rule over here to get alpha 0 vector plus alpha 0 vector. But now we can use our cancellation rule to cancel this alpha 0 vector from both sides, leaving us with just the 0 vector on the left-hand side. So that'll give us 0 vector equals alpha 0 vector, which is exactly what we wanted to end up with. Okay, nice. So now let's look at this second one. This says that if we take the scalar 0 and multiply it into any vector V, we get the 0 vector. So notice I've got the scalar vector 0 here and the vector 0 vector there. So notice I've got the scalar 0 here and the vector 0 here. So it's really important to distinguish that for this one. But the proof is going to follow pretty similarly. So let's take 0v. Notice we can write that as 0 plus 0v, because 0 is the additive identity of the field. Here we use the fact that 0 vector was the additive identity of the vector space. But here, 0 is the additive identity of the field. Okay, now we'll use one of these distributive rules over here to rewrite this as 0v plus 0v. Then we'll do a cancellation just like we did before. We'll cancel this with this. That'll leave us with the 0 vector on the left-hand side. So we have the 0 vector is equal to 0 times any vector v. Okay, so that gives us this second result. Okay, let's maybe clean this up and we'll look at the third result. So now let's look at this third one. This says if we take the scalar minus alpha, do scalar multiplication of minus alpha with v, it's the same thing as doing the scalar multiplication of alpha with v and then taking the additive inverse. That's how we would read that. Okay, so let's maybe see how we would do this. Let's start with alpha v plus minus alpha v. I think that's maybe a good place to get started with this. Then we can use our distributive rule like this over here to rewrite this as alpha plus minus alpha v. So this is vector addition right here, but now this is scalar addition. But since this is scalar addition, we know that this is going to be equal to 0v, which is equal to the 0 vector. Then we can finish this off by subtracting alpha v from both sides. And that will give us minus alpha v equals minus alpha v. That's what we get from subtracting minus alpha from both sides of this equation. Okay, so that gives us this one right here. So now let's look at this last one. It says that alpha v is equal to 0. I guess I should say this is the 0 vector, if and only if alpha is the 0 scalar or v is the 0 vector. Well, this is an if and only if statement, so there are two things to prove. Let's talk about the reverse direction first. And notice that that is done by, maybe I'll underline these in this green color, what we saw right here and right here. So it's done by those first two results. Okay, so now let's do this forward direction. So let's suppose that alpha v is equal to the 0 vector and see if we can get to alpha equals 0 or v equals 0. Now we're going to do a pretty interesting method of proof here. Notice we want to end with this or statement. So we'll start by assuming one of them is not true and showing that the other one must be true. This is like breaking it down into two cases. So we might notice that case 1 would be something like alpha is equal to 0, but in that case we are done because we've achieved one of the statements from this or statement. So let's move on to case 2, which is alpha is not equal to 0. But if alpha is not equal to 0 in the field, then it has a multiplicative inverse. So let's write that as there exists alpha inverse in our field K such that alpha inverse is equal to 1 in our field K. Remember, in a field, everything which is non-zero has a multiplicative inverse. Okay, nice. So now let's take this equation right here and multiply both sides by alpha inverse. So we have alpha inverse alpha v is the same thing as alpha inverse multiplied onto the 0 vector. But by this one right here, we know that that gives us the 0 vector. But then by our associativity of multiplication, we can rewrite this as alpha inverse alpha v equals the 0 vector. But alpha inverse alpha v is exactly 1. So we have that's the scalar multiple of 1 with v equals the 0 vector. But by our condition over here for our vector space, the scalar multiple with 1 is just the vector itself. So we end up with v is equal to the 0 vector. So let's just reiterate what happened. So alpha could either be 0, in which case we're done, or it could be non-zero, in which case we have some work to do. But we've shown that if it is non-zero, then v is equal to 0, which is the other portion of our or statement. So either way we get to it, if we start here, we end with one of these statements. Okay, so let's get rid of this and I'll leave you with some warm-up exercises. So here are some nice warm-up exercises. The first is to fill in all of the details that Kn and K adjoin X are vector spaces over K. So we waved our hands at most of the properties, but it's a very good exercise to just really check that all of these are satisfied. So there are a lot of details to check, and again, I think you'll get a lot out of it. The next is to do kind of a symmetric property to one that we just proved, and that is if we have a vector space V over a field K, alpha is an element from the field and V is an element from the vector space, then the scalar multiple of alpha with minus V is the same thing as minus alpha V. Anyway, so this should go pretty similarly to what we saw before. Then finally, show that C, the complex numbers, is a vector space over R. So again, you'll have to check everything over here, just like you checked those for these two up here. Okay, that's a good place to stop.